Welcome to a new episode of TTTribeCast. In this session, we will hear from Bas Dijkstra on an introduction to mutation testing.
So, welcome to this webinar on mutation testing by Bas Dijkstra. So, before moving on, a huge shout out to BrowserStack, our exclusive sponsor for all community events and premier sponsor for all conferences. We thank them for their support, because of which we are able to do all these events. Now, a little bit about our speaker. So, our speaker, Bas, he's an independent test automation consultant and trainer. He has been active in the test automation field for 16 years now and has worked on software testing and automation solutions across a wide range of programming language frameworks and technology stacks. I would like to welcome him up on the stage to share his knowledge on today's topic, that is Introduction to Mutation Testing. Subhas, welcome to the stage.
Thank you so much, Vanshika, for that introduction. And thank you so much for having me. And it's so wonderful to see all of the activities that you're undertaking, all of the events that you're organizing with the community. It's not the first time I've been involved with the Test Tribe. Hopefully, after this one, you'll have me back for a future event somewhere, sometime.
Sure,
but for
definitely.
for today, I'm really excited to join you and to talk to you. Let me share my screen for a moment. Let's get started then. So, what I want to talk about today, what we promised you to talk about today is mutation testing. But I want to start off before we dive into the topic, into the technology, and into the fun stuff. And before we dive into telling you what mutation testing is, how it works, and what it looks like, I want to talk a little bit about the importance of testing your tests first, because just throwing tools at a problem is never the right idea. It's probably a good idea to talk a little bit about what's the problem that we're actually trying to solve here. But I'll promise you after the slide where we'll dive into the code and you'll see mutation testing in action. Absolutely. I'm not going to add anything to the introduction that Vanshika gave me. Because, well, that's boring, really. So let's talk about testing and automation and mutation testing right away. So this is the world we live in these days, a world of continuous testing. We test everywhere and we test all the time. And more teams and organizations are calling the help of tools to support that testing, which not coincidentally is my definition of test automation. It's using tools to support your testing efforts. But that's and we want to do more of that because we need to test smarter. We need to test more. We need to test more efficiently, and we need to test everywhere, everything, all the time. That's also typically referred to as continuous testing, which means we'll run tests on local development machines. We test in production, and we test anywhere in between. Test or acceptance environments, staging environments, pre-production environments, you name it, we test there. And as I said, we use more and more. We rely more and more on automation to help us do that testing more efficiently. We write scripts to help us gather information about the quality of a product, and close and shorten that feedback loop, get faster feedback about the quality of our product. So we write scripts, we automate test cases, we write code that helps us, again, get information about the quality of a product. So we do a lot of automation, but there's one thing, and we rely more and more on automation to help us make that decision about, is the quality of our software good enough to promote this build, this release, this increment, this whatever, to the next stage in our delivery pipeline. And the next stage in that delivery pipeline might just be your production environment. So we rely more and more on automation, automated tests, to help us make that decision quickly and efficiently about what's the quality of a product. Is the quality of this product, is this good enough to promote this to the next stage? And again, that can be production. So we spend a lot of time writing automation and getting to a specific level of coverage, for example. But what I feel, and again, this is me talking about myself in the past and a lot of people and teams that I've worked with, and the way I see a lot of people talk and discuss automation. There's one thing I feel we're sometimes forgetting or not taking enough time to do, and that's having a close look at the quality of our tests themselves, because we rely more and more on these automated tests to help us make that decision about, is this good enough to go into production? But we don't spend enough time talking about working towards better quality of our tests. So we're building a safety net with our automated tests, but we don't really have a clue about what the quality or the durability of or the reliability of that safety net really is. And automation, again, automation is software. Software can contain errors, defects, bugs, whatever you want to call them. And with automated tests, these can come in two forms, really. False positives, which is a test that fails when your application works as expected. Meaning my test fails, but the reason for my test failing is not a defect in my application. It means there's something wrong with my test itself. Sometimes that's continuously, so a test that fails all the time, to which my first question would be, in response to that, would be, why didn't you fix it? And by fix it, I mean either fix it or just throw that test away, because a test that's continuously failing, it's only noise. It's not giving you any valuable information at all. Or tests that fail every now and then. So sometimes they fail, sometimes they pass. And you might know them better as flaky tests. So tests that have different that produce different results, different information, when there's not really a change in the application or in the system that it's testing. So there's a number of different root causes for these false positives. It can be problems with your test data. It can be problems with your test environment, so some kind of third-party system or some other kind of dependency or component that you rely on in your testing that's behaving weirdly, or that's not available, or that's just responding very, very slowly. Or there's a problem with timing or synchronization. So you try, and UI tests are famous for this. So you try to click a button that's not yet visible. You try to fill in text into a text field, but there's like a modal or an overlay that's blocking access, even though you think it's visible and enabled, but it's really not. So, and these are just some of the main categories of reasons why that produce these false positives that say, well, oh, my test failed when, well, there's not really something wrong with your software. It's just, well, the data in there wasn't the data that you expected, or something downstream in your test environment didn't work as you expected, or that screen that took a little bit longer to load than you expected in your test. False positives are annoying because they generate a lot of noise and they scream, oh, I failed each and every time, where there's nothing really wrong with your application. But there's also false negatives. And false negatives are tests that pass, but don't detect the bug in your code that they're supposed to, that you thought they would detect. Or don't detect the change. That's maybe a better wording. It's up to humans to decide whether or not an unintended is a bug. But they don't detect the change that you think that they were supposed to detect. And again, while false positives are annoying, at least they make themselves known. They present themselves because, well, there's a failing test. A false negative is, well, what I call a silent killer. It's a test that passes, so it shows these green check marks. Everything is green. It looks like everything's in order. And then your software goes into production, and the first time an actual user and an actual human being interacts with it, everything breaks down. Even though you thought you had it all covered with your tests, the quality of your tests isn't good enough. And this is why I think we should spend a little bit more time sometimes talking about investigating and improving the quality of our tests. A quick example. So we have a class that represents a bank account here. A bank account has a type, it has a balance, there's a constructor, and there's this method that adds interest. And it uses an interest rate for that. But the clue here, the key here is we can only do this for savings accounts. So presumably there's also other types of accounts like checking accounts or investment accounts, or I don't know what kinds of accounts. But calculating interest can really only be done on savings accounts. I know this is not the best way to implement it, but, well, it's more about the point than the actual code. And we've got a test. We've got a test that checks, well, if we create a new savings account type, deposit 10, add interest, add a 5% calculate interest with an interest rate of 5%, then our resulting balance should be 1050. Sounds like a valuable test. Sounds like a good test. Test passes, and yay, 100% code coverage, because this test covers all of the code here. And this is what a lot of people rely on, what I see a lot of teams rely on tests that pass, yay, and we've got 100% code coverage. So therefore, our test must be good, right? Now imagine a developer coming in after a particularly long weekend of lots of partying and not so much sleep, and saying, well, time to refactor some code or improve some code, and they start making some changes, and they make a mistake. I don't know if there are any developers in the audience. I'm not talking about you. I'm talking about the other developers. You don't do that. But developers sometimes make mistakes. And let's say they accidentally refactor, and they refactor this clause, this condition, so that it always returns, always evaluates to true. It happens. People make mistakes. Other people make mistakes. So they do their refactoring, and they rely on their tests as safety nets. Makes sense. But problem here is the tests still pass, and there's still 100% code coverage. So they push stuff into production, and what do you know? Suddenly interest is calculated not just for savings account, but for all accounts, meaning, well, lots and lots and lots of money will be lost. Not something that you would want to happen on a Monday morning. So this is just, again, it's a pretty trivial example, but this is hopefully an example that makes you aware, and that hopefully helps you realize that just relying on tests that pass and just relying on code coverage as a metric to talk about the quality of your tests, probably not a good idea. Much smarter people than myself have talked about this in the past as well. I stole this little image from, I think it was Uncle Bob or Martin Fowler, one of the two. I can't remember, on all honesty, but one of the two said, well, test coverage is a perfect way to find code that's not tested yet. But as a quality target or as a quality metric in and of itself, it's useless, because code coverage, or any type of coverage really, is a quantitative metric. So it tells you about how much of something you've done. What it doesn't tell you is, it doesn't tell you anything about the quality of the work that you've done. It doesn't tell you, in this case, it doesn't tell you anything about the quality of the test. It tells you something about the quantity of the tests and the quantity of the code that you've exercised with your tests, but it doesn't tell you anything about the quality. Um, so we should do some more work probably on trusting our tests again, and making sure that we can actually trust the work that we do, trust our tests. Which probably means it's a good idea to test your tests, to make sure that you don't just have a lot of tests, but also that the quality of your tests is good enough. Some of the things that help a lot here is code reviews, or just pair programming. Periodically testing your tests and make sure that they still do the stuff that they're supposed to do. Meaning reviewing your test suite often, not just when you create it, but also over time, because code evolves and tests evolve. So I like to periodically go through my entire test suite, and for each and every test decide, well, is this test still making me happy? Is it still giving me information that's important to me? And can I still rely on that test giving me the information that I'm looking for in a reliable and efficient manner? So reviewing is a good way. And of course, I don't want to go all Marie Kondo on you, but if it doesn't spark joy, just throw tests out if they don't make you happy anymore. Don't be afraid to throw them out. Don't fall for that sunk cost fallacy of, oh, we spent so much time writing these tests and now you're telling us to throw it away. Yes. If it doesn't give you any value anymore, just please throw them out. And also, this is one of the first things I teach people when I teach them automation. If they written their first test and the code compiles the first time, and you see a green check mark in your IDE, that's where you start distrusting yourself. Because are you really sure that your test is testing the things that you think it's testing? It's probably a good idea to make sure that your test can actually fail. Never trust a test you haven't seen fail. If it compiles the first time, it passes the first time, it's probably a good idea to have a closer look and see, well, did I actually implement that the way I thought I implemented it? And is it actually checking what I think it's checking? Because trust me, I've been there. I've written tests that I thought did a lot of good stuff, and then turned out they didn't do anything. They didn't say, okay. That sounds like a lot of work, and it is. But lucky for us, there are tools that can help us do that, help us test our tests. And this is where we start talking about mutation testing. Mutation testing is a technique supported by tools that can help you get a better insight into the quality of your tests and help you make sure that the tests that you write are actually effective and efficient at finding changes, finding potential defects. Um, the way it works, the way mutation testing works, is it inserts small changes into your application code. So it makes deliberate changes in the source code of your system. These small changes, they are referred to as mutants, hence mutation testing. Um, you then run well, it says unit test here. It can really be any type of tests, but it's just computationally most efficient to do it with unit testing. But the concept works for other types of tests as well. So run your tests against the modified code. And if a unit test fails, or rather, if a change is detected by at least one of your unit tests, that's a good thing because it means your unit tests picked up on a change. If your unit tests keep on passing, or rather, there's a change that's not detected by any of the tests, that's worth an investigation. So, if the mutation testing tool is able to make some changes into your code that are not picked up by any of the tests, that might just mean that your tests are not effective enough. But that's just one of the potential outcomes. We'll talk about. You'll see a couple of potential outcomes and results from mutation testing signals in the demo. We'll go into the demo in a couple of minutes. But if your unit tests keep passing, or rather, if there's a change that goes undetected by your unit tests, that's worth an investigation. It's time to do some work there. There's lots of different tools for mutation testing out there. The tool that I'm going to demo today is called pitest. Pitest is a mutation testing library for Java. So it mutates Java code. It mutates Java bytecode, to be more precise. It injects small changes and then runs your tests, and it basically does the mutation testing process for you. Like a lot of mutation testing tools out there, it emerged in academia. So there's a lot of academic research going on around mutation testing. And there's a lot of different tools that emerged from academia in the mutation testing area. PyTest is one of the few mutation testing tools that's actively supported also by industry. You can tell, so that if you see the reports, you can tell it comes from academia because nobody paid any attention to how the reports look. I actually kind of like it because it gives off a distinct 90s vibe, the reports, but it is actively supported. It's actively used also in the industry, which I think makes it a great candidate for a demo. It's also open source. It's pretty easy to configure, which isn't true for every mutation testing tool, but PyTest is actually pretty easy to adopt and get started with. And if you want to know more, there's a website, of course. Of course, there's a website. So configuring PyTest or Pit is just a matter of adding a plugin to your project. And there's a configuration section in there that you can use. So you can say, well, I want to use the default, a specific set of mutators. And mutators are the kinds of changes that the mutation testing tool makes to your code. I'll show you the defaults, but there's lots of others. And you can tell, for example, where the code that you want to mutate is located and where the associated tests are located. So it's probably, I'll talk a little bit more about that at the end of this session, but it's probably not a good idea to just run mutation testing on all of your code right from the start. Because A, it's probably going to take a very long time, and B, it's going to generate a lot of noise, a lot of signals that you then need to figure out. So it's like with all things, it's a good idea to start small, see if it's valuable to you, and then keep using what you like and stop using what you don't. I'll just go over this in the code. It's time to stop looking at slides and start looking at code. This is the project that I prepared that I use in these sessions. If you, it has an account class, which again represents that same bank account. There's methods to get the balance. I can deposit stuff. I can withdraw stuff. I can add interest. I've got some supporting classes. And of course, most importantly, I've got tests on that test the implementation of this, or test the behavior rather of this account class. And of course, I've got pitest added to this project here using the same configuration that you just saw in the slides. I want to run, just to prove that my tests are running, I'm going to run the tests first. Yay, IntelliJ is deciding to be slow again. So I've written tests. I spent a lot of time writing my tests, making sure my tests are right. And yay, all my tests are passing. And now I run mutation coverage. There we go. This arcane command runs pitest on my code. So what it does, it generates in memory. So it doesn't actually change the source code. It generates in memory mutants of the source code. So it creates small changes like flipping a binary operator or removing a call to a method that returns nothing. So return with a void return type, all those things. And it checks if there's at least one test that detects that change. And then it reports on the results. So the reports end up in here. So let's have a look at those in my browser. Here's where you can tell not a lot. This tool already originated somewhere in academia. The report is functional but not very fancy. However, if we zoom in on the results, there's some very interesting information in here. So, as always, green is good. It's the red, well, pink, salmon-ish things that you need to investigate further. So, for example, what the mutation testing tool did here is it replaced the double with 0 for the account. So it replaced this with just return 0. And it checked, well, is there a test that picked up on this? And yes, there was. So this mutant was killed, as you can see in the description. However, there's also a couple of mutants that still survived. So let's look at this one, for example. There's dark pink and light pink. Light pink thing, let's investigate that light pink first. That's just a coverage issue. So mutation testing does code coverage, calculates code coverage as well. But it does more than that. So let's address this one first. This tells me this wasn't covered. And that's true because I don't have a test that tries to call the add interest method on an account of type checking, and then checks that the right interest exception is thrown. So let's add a test that does that. So I'm going to add another test here that says void add interest to checking account. Don't look at the typos too much. It's not that important. New account with a checking. Oops, that's not what I wanted to type. There we go. And I want to assert that when I call the add interest method on this account, and I can even shorten this further. I want to make sure that if I call the add interest method on an account of type checking, that the add interest exception is thrown. So let's just before you start mutations, please make sure that your tests still pass. That your tests actually do. Okay, so I've got an extra test now that passes. So let's run pitest again to see if there's an improvement in my mutation testing results. And there should be. There we go. Let's look. Oh, come on, refresh. There we go. And let's have a look at it. Awesome. So this is now green, which means it's covered. And this one is killed, where previously this one survived. So we improved our test suite. However, this is any basic code coverage tool can do this. So what makes mutation testing more valuable than just doing code coverage? Well, for example, let's have a look at this one. It says, well, if I remove this call, this one isn't covered. So, and if I look at my code, it even tells me, well, that's true because this method is never used. So, and of course, this is a small code base, so I could probably have seen this just in my ID. But if you have a larger code base, it's code like this goes by undetected. So maybe one of the potential outcomes of a mutation testing run is one of the potential things that potential results is it detects that unused code. So let's remove that. And again, tests first to see if it doesn't have an adverse effect on our test. Well, it shouldn't because that code is never called. So our tests still pass. Yeah, so we have code coverage now as one of the things that mutation testing does, and finding that code. Awesome. So let's open this one too. No, that's probably not there anymore. And you can see this one is just this call on line 30 is now just gone. It's no longer there. I don't have time to go into to fix all of them. We've only got 1 hour, but there's one final one that I put the most interesting one that I want to go into right now, and that's this one. So for this, this withdrawal method has a bit of business logic in there, and basically it says if the amount you want to withdraw is greater than the current balance and the account type equals savings, it should throw a withdraw exception. Which means basically you cannot overdraw on a savings account. Well, that's the logic that's implemented here. However, what this tells me is that, well, it removed a conditional. So first it removed this one, and then it removed this one, and those two were killed, which means that those changes were detected by at least one of the tests. However, the top one says, I changed the conditional boundary and it survived. What it did is it replaced this greater than sign with a greater than equal sign. And that, again, I think that's a small change with potentially very big implications. That's very easy to slip by undetected. And our current set of tests, well, they cover this logic because it's green in here, so it's covered. But that change that was injected, that was generated by the mutation testing tool, is not detected. So this being changed into greater than equals isn't detected, which means we probably don't test very well, if at all, around the boundaries of this clause, around the boundaries of this clause. And if we have a look, if you have a look at the test code, you'll see that there's only really, let's have a look at the tests. There's some withdrawing going on here, but there's no test that actually tests to the boundary of this clause here, which can potentially have some very, very interesting undesired results and effects. So this tells me I probably need to do some more testing around the boundaries. And in this case, I can change this by, I can easily solve this, knowing that you didn't know that. That's why I'm telling you now. If I create a new account and if the account type is savings, the initial balance is 10. So new savings account are loaded with 10. By default, it's a gift from the bank. And I don't know if there's no banks that do this anymore, but over here in the Netherlands, banks used to do something like this. And checking accounts are just loaded with a bank with an initial balance of 0. Which means I can easily withdraw, just create a new savings account. Then withdraw 10 because the balance is 10. So this is right spot on the boundary value of this clause that you saw here. And then check that it's equal to 0. Now, let's run. Oh, no. Just repeat prior. Don't type all the commands again and again. Let's run the test again. Well, this basically says, well, 10 minus 10 is 0. That's still true, luckily. And now let's run our mutation testing again. Good thing to know is every time you run your mutation test, it's deterministic. So it'll generate the same changes each and every time, which and so it's a repeatable process. It's deterministic. Let's open the latest report again and have a look here, and we can see that so line 46, where this one, in this case, that change of the conditional boundary survived. So the change from greater than to greater than equals was not detected. It is now detected because the mutant is killed. So we now have a test that has better coverage around the boundaries of this logic, which I think, and because it's often these boundaries where things start going wrong. So it's probably a really good idea to have solid tests, especially around the boundaries of this logic, of these conditions. And mutation testing is a great way, a very efficient way of making sure that your tests actually cover that to a decent extent, so to say. I'm not going to be able to cover and fix all of these, but just know that these ones are also have to do with conditional boundaries. And these ones are just, well, there's a transaction list. So basically a ledger of all the transactions that happen for a certain account. Um, the mutation testing tool removed the call to removed this entire method call, but that wasn't picked up by any of the tests. And if you have a look at the tests, and I'll give you the link to the GitHub repository in a moment, so you can have a look for yourself and experiment with mutation testing a little bit for yourself. You'll see that the tests don't really cover this. They don't check the check the transaction list to see if the transaction that you just made was added to the list. Which also, so your test spot, it's something that you probably want to test, but maybe you didn't think to test it. And mutation testing tools can help you uncover things like that. I know we've got we'd like to spend a couple of minutes on questions. So let me just wrap my yammering up by rephrasing that. I hope that this short demo gave you a first impression of some of the things that mutation testing can do. I think it's potentially a very powerful technique that I don't see used very often. And I saw I love how the people at the Test Tribe actually did their homework and pulled up some research that said that there's not really a lot of teams and organizations that use this. But I hope that this short demonstration has shown you some of the interesting results and some of the interesting information that mutation testing and mutation testing tools can give you about the quality of the tests that you actually write. And just know that, well, they do everything that code coverage tools can do. As you can see, well, they detect gaps in your coverage. But there's also quite a few things that mutation testing can do for you that code coverage just doesn't. Code coverage doesn't tell you anything about how well you test against the boundaries. Code coverage doesn't tell you anything if on the result of removing certain method calls, for example, if those are detected by your tests. So mutation testing is much more a qualitative way to assess your tests as compared to code coverage, which is really only giving you quantitative information about the amount of tests that you run and the amount of code that was exercised, but it doesn't tell you a lot about the quality of the tests that have been executed. And mutation testing does. A few quick implementation tips before I wrap up. Don't mutation test all of your code, especially not when you start, because the more code you mutation test, the more mutants will be generated, and all of your tests will be run for all of your mutants. So execution time can potentially explode. You didn't really see that in the demo because this demo was very small. It's only 8 tests and only like 120 lines of code. But if you have a large code base and a large test suite, your mutation testing execution time can potentially explode. So my suggestion would be to start small. Start on a small but important piece of your code and see the value that mutation testing brings. And I think it works especially well for things like algorithms, business logic, exactly the kinds of things that I showed you in the demo, these business rules and the tests around those business rules. And I think mutation testing is a great way to make sure that the tests that you write around those crucial parts of your application code are actually trustworthy, are actually giving you the information that you're looking for in a reliable manner. Um, if you want to play around with the code that I've just shown you yourself, you can find it on GitHub. It's all on there. PyTest is open source, so if you're working in a Java project and you say, "Well, I want to have a look at what mutation testing can bring for me," just add PyTest to that project. Just add the PyTest the Maven plugin, and have a crack at it. Really. Um, that's it from me. Vanchika, are there any questions, any comments, anything that warrants a reaction?
Yeah, so we have few questions. I'll just share them.
Yes, please.
So we have a question from Matthias. Uh, so thanks for a very interesting talk. What are the advantages of using mutation testing instead of extending the measuring of test coverage from the line coverage to also measure? Example, branch coverage as well.
That's a very good question. So basic line coverage is, well, as the question answered, that's the most shallow coverage metric. So branch coverage is already more reliable, but that still doesn't take into account the boundaries typically. So it only says, well, if there's a branch with branch coverage, you just assert, well, we went left once and we went right once in that branch. But it typically doesn't really, unless you again because you're really careful, it doesn't really take into account the boundaries, as well as mutation testing does. And again, add that those tests again around the boundaries is just one of the several, maybe even many different kinds of quality issues that mutation testing can do. Um, but if branch cover, if just measuring branch coverage is enough for you, and you're absolutely sure that that's enough, then maybe that's enough. I'm not saying that everybody should definitely always use mutation testing, but I'm sure that there's things that mutation testing can do that different types, any type of coverage just cannot do for you as efficiently.
Understood. Got it. We have a question. We have few questions from Abhijit. I guess we'll take all of them. So the first question he has is, how is mutation testing deterministic? How does it decide internally where and what to mutate?
That is a very, very good question. So it is, and it is, so it will generate the same changes each and every time. So it doesn't just randomly change things. There's a set of rules, um, that you add, a set of mutators that you can configure. As I said, I loaded the default set of mutators. That's a predefined list of, these are the changes that I'm going to make. And so for example, each and every time the mutation testing tools encounters a greater than sign, it's going to change that into greater than equals every time without exception. And it will do that each and every time you run mutation testing on your code base, which means that every time you run on your code, it will generate the same collection of mutants. And it does that again through that list of mutators. So defaults is, well, it's all in the name, a set of default mutators that's applied to your code. It's like 20 or 30, I don't know, I don't remember exactly, but around 20 or 30 different. So if it recognizes a pattern or it sees a certain symbol and a mutator is activated, it will change that. It will apply that rule to that operator, to that operand, for example. I hope that's clear enough. So it uses a preloaded set of mutators, and a mutator is applies to a certain type of operator or a certain type of pattern in your code, and each and every time that pattern or that operator is in your code, your mutation testing tool will apply that mutator to that code.
Understood. I hope, Abhijit, that answers your first question. There's another question from him. So, are there any scenarios in which mutation testing can generate a lot of noise? Basically, changes done by mutation testing, can they be invalid? Maybe it crashes the app too often.
I don't know about crashing the app, but yeah, there's definitely some scenarios in which mutation testing can generate a lot of noise. So I didn't really show that in the demo, but there's another class in there as well. And I invite you to just clone that repository and run mutation testing for yourself and inspect the results. There's a transaction class in there, which is just a basic, a plain old Java, a Pojo or a Java Bean, whatever you want to call it, which has some getters and setters. It's not a very good idea to run mutation test because maybe not all of the getters and setters will be executed each and every time you run your tests, or maybe they will not all. They're just there for serialization purposes, for example, and not all of your tests exercise the getters and the setters. That will generate signals from from your mutation testing tool. But that doesn't mean that you should just start writing tests that test getters and setters for your code. So that's one of the main examples, one of the most common obvious examples where mutation testing generates noise, which is why you probably want to exclude those classes and the packages that contain those classes from your mutation testing efforts. Yeah.
Understood. So another question we have is, what are the tools for C, C++?
Ooh, I don't know. One moment. So I know of a, no, it doesn't. I don't know, but and I'm literally just Googling it right now. I'm sure. Oh, there it is. So, is there a chat that I can dump link in? That probably is, right. This one is for C++. There, I dropped it in the chat, not in the Q&A. Sorry for that. Again, just a 5-second. I'm not a C or C++ programmer, so I've never worked with those. I've not touched C since university, and that's a couple of years ago. So I'm not familiar with any. I don't have first-hand experience with those tools, but they exist. They definitely exist.
Understood. One last question from Asma. So how do we implement this? Is it best to have both engineering and QA automation team to work on this testing together, or who should take the lead of this?
Um, so there's not. I don't think there's a stock answer to this question. It's just another form of testing and automation. So my stock answer would be the team, but that's not very helpful. So mutation testing works with. So I've demoed it with unit tests, and why with unit tests? Because that's um, the most computationally efficient, because again it'll potentially generate lots of mutants, and it will run your entire test suite on each and every mutant, which again can make your test execution time explode. So it's definitely a good idea to start with your unit tests. It's not limited to your unit tests, it's just you get the quickest results there, which sort of imply that it's the people who are responsible for writing and maintaining and running the unit tests, which typically are your developers. But that doesn't mean that testers should not be involved in that. So, well, oh no, that's development responsibility, so let them do it. That would be and that's why I sort of kind of half jokingly said the team, but it's all a team effort. So, but it's a great idea to. I think it's a great. This is one of the things that potentially can um, help developers do better and more testing too, because it gives them tools, and they like tools. Everybody likes tools, to help them do better testing or write better tests. So, and I think that helps everybody in the end.
Understood. I think that answers all the question that we have here. Yeah. So I think that ends it. So thank you so much, Bas, for doing this webinar with us. It was a great session, a great knowledgeful session, and I can see in the chat people are loving it. Like this whole session, they were hooked on to every word, and they love the session a lot. So thank you so much for doing this and presenting your knowledge with us. We will meet in another session in some with some new topic, another interesting topic. Till then, keep learning, and thank you so much for joining in.
Thank
Bye.
you so much to everybody for taking the time out of your day. I really enjoyed it. Thank you, Vanshika, and the rest of the Test Tribe team for having me. We should do this again sometime. I loved it.
Yeah,
Thank you so
sure.
much. Have a great day. Have a great evening, everybody. Cheers.
Bye.
Bye bye.